Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Today your lesson deals with molecular geometry and intermolecular forces. In this lesson, we will be talking about electronegativity, bond polarity, polar bonds in diatomic molecules, polyatomic molecules, the Vesper theory, molecular geometry of polyatomic molecules, polarity of polyatomic molecules, and there's a summary table. Today's lesson starts on page 62 and ends on page 74 from the text Chemistry 11 in Focus. Knowledge of molecular geometry, I can't read well, the three-dimensional structure of the atoms in molecules, is important since it helps to predict the polarity of molecules, the type of intermolecular force that exists between molecules, the boiling and melting points of compounds, the solubility of compounds in other compounds, and their reactivity. New molecules can be created with specific shapes and polarity to achieve some desired effect. The antibiotic penicillin, for example, has been modified to become ampicillin, a more effective broad-based antibiotic, by the addition of an amino acid chain to it. Many diseases are treated with drugs whose molecules have been specifically designed to destroy viruses and bacteria or to influence the metabolism of cells in specific ways. Many drugs are designed to act as inhibitors of enzymes by blocking their active sites to achieve some desired effect. Drugs for treating HIV, infection, hypertension, and erectile dysfunction in men work on this basis. Knowledge of the enzyme structure and shape and the nature of the active sites are important in this respect. In protein synthesis, transfer RNA molecules choose the correct amino acids because of their specific shapes. Any mistake in choosing the correct amino acid could lead to the formation of dysfunctional protein. These are just of the many ways that knowledge of molecular geometry is important. Our first concept that we'll discuss today is that of intermolecular force of attraction. But before we get into that, we have to do some preliminary work. Now there's something called electronegativity. Electronegativity is a measure of the ability of an atom in a molecule to draw the bonded pair of electrons to itself. The bonding electrons are in the form of an electron cloud of specific shape. In 1992, Linus Pauling, an American biochemist who was the recipient of 2 Nobel Prizes, developed an electronegativity scale for the elements. So you're going to see this table below here gives the electronegative values he assigned to some of the common elements. So we use this as the basis for our lessons. All the elements in the periodic table, each one of them has been assigned an electronegativity value. So for now, you can see that as you move that side here, the electronegativity value decreases. So fluorine has the highest electronegativity value, okay? And apparently potassium here has least electronegativity value. Don't worry, you understand it as time goes by. Bond polarity. Just like a magnet has 2 poles, molecules also have a little bit of electrical polarity. They can or not, depending on some of the features of the molecule, right? Now, for diatomic molecules, what I mean by diatomic molecules? Molecules with only 2 atoms. For example, these here are diatomic molecules, only 2, right? Whether a covalent bond is polar or not depends solely on the difference in electronegativity of the two bonded atoms. In homonuclear diatomic molecules, molecules containing two identical atoms, so these are examples of what we call homonuclear diatomic molecules, hydrogen and chlorine. Since there is no electronegativity difference between the bonded atoms, the bond is no polar. Hydrogen and chlorine molecules are used to demonstrate this concept. This is the electronegativity value for hydrogen, and that is for chlorine, the other one here. Now, this is the bond here, and this hydrogen is pulling on the electron cloud here with that degree of a kind of force, and that one exactly is the same electronegative force. The electron cloud in between here will not shift either in that direction or this direction. The difference is 0. Same thing will happen here, 3.5 and 3.5. All homonuclear diatomic molecules, N2, Cl2, H2, O2, Br2, in all of these, the bond will be non-polar because there's no difference in electronegativity between these atoms here. Now the difficulty arises when you're dealing with other molecules that are not homonuclear. Alright, we come back to this concept of electron cloud again. That's why I'm introducing the idea of electron cloud, because that's the only way we'll be able to really get a good understanding of some concepts in chemistry. Both of these molecules are nonpolar because in each there's an even distribution of the shared electron cloud between the two bonded atoms. So this is being depicted here. This is a hydrogen here and there's another hydrogen here. There's an even distribution of electron cloud between there, these atoms there, and the same thing here. Heteronuclear molecules. Molecules where there is two different elements. If the electronegativity difference between two bonded atoms is greater than 0.4, then the covalent bond becomes polar. For those that we dealt with before, there was no electronegativity difference. However, if you have heteronuclear molecules and you find that there is a difference in electronegativity between these two bonded atoms that is greater than 0.4, then the bond becomes a polar bond. And the example I'm using here is hydrogen and chlorine. You bond these together. Now you're having hydrogen with an electronegativity of 2.1 and chlorine 3.16 electronegativity value, sorry. So the difference here is 1.06. Definitely now this bond will be polar. And let's see why it is called a polar bond. Let's read this paragraph here and maybe it will make some sense for us. The bond between hydrogen and chlorine atom is polar because the chlorine atom, which is significantly more electronegative than the hydrogen atom, exerts a greater pull on the shared electron cloud. Because of this stronger pull, more of the electron cloud stays with the chlorine atom, causing it to acquire a partial negative charge, symbolize this, delta negative, and the hydrogen atom to acquire partial positive charge, symbolize delta positive. This is usually what happens in heteronuclear diatomic molecules, molecules containing two different atoms. The greater the electronegativity difference between the atoms, of course, the more polar the bond becomes. Alright, so let me lead you on to this electron shift a little bit. Let us suppose that we have a hydrogen atom here, right? Recall that hydrogen atom has one proton. The nucleus is always positively charged for any element. And around here you have this negative electron cloud, right? Now imagine what will happen if you pull that cloud a little bit away. So if you drag the electron cloud a little bit towards that side of the atom, we're actually now isolating this positive charge. Before, this positive charge was equally neutralized by the electron cloud because it's exactly in the center of the atom. If we shift the electron cloud a little bit more toward that side, we are isolating this positive charge, so some degree of positive characteristic is manifested on this side here. And that is why we call it delta positive, a small positive, and that will be delta negative. The greater the shifting of the cloud, more of the positive becomes manifested on this side, and more of the negative becomes manifested on that side. So this is generally how shifting of the electron cloud, any molecule or something like that, will cause one end to become slightly negative and one end slightly positive. I'm using hydrogen chloride here to illustrate this concept. Before this was hydrogen, see how symmetrical this cloud is? And this is chlorine. Before it reacted, see how symmetrical that cloud is. But when you bond them together, because of the greater electronegativity of the chlorine has a greater, say, greed for electrons. So what it does, it pulls more than its fair share of electrons towards its own side here. When that happens, as I explained before, it leaves this side with a slight positive charge, and this one here will acquire a negative charge. Of course, now this is a little scale here that we have here that shows you what happens when there's big difference in electronegativity or when there's no electronegativity difference in atom. So you start from 0 here and you come to 3.3. That is difference in electronegativity, right? If you have any molecule that has a diatomic molecule, of course, and the atoms have a difference in electronegativity that is less than 0.4, you consider the bond to be a pure covalent bond. All right? If now the difference in electronegativity is between 0.4 greater than that and 1.7, the bond that is formed between those two atoms there we call a polar covalent bond. However, when it starts to get greater than that, then more electronegative atom, it actually takes the entire electron away. In this case, chlorine takes the entire electron away from the hydrogen, if ever that would ever happen. I'm just using it as an example. If that was so strong, it can take the electron away from the hydrogen. And here you end up with an ionic bond because you're making ions here. Okay? So I hope this little scale will help us to determine whether covalent bonds are polar or not. So you're asked to do that. Exercise this. You can check the solutions manual for this solution, for the solutions and answer to that. Diatomic molecules, there are some summaries that we make about them. Good. These are all. If the molecule is homonuclear, of course, the bond is nonpolar. There's no difference in electronegativity. So the molecule must also be nonpolar. So if a bond within a molecule is nonpolar, then the molecule itself becomes nonpolar for these homonuclear molecules. If the molecule is heteronuclear and the bond is polar, the molecule is also polar. And you have these as examples here. Examples of these are hydrogen bromide, hydrogen fluoride. If you check the electronegativity difference between these, you'll find that the bond will be polar because the difference is greater than 0. We're talking about diatomic molecules here. If the bond is polar, the molecule becomes polar. This does not apply to when you have polyatomic molecules. In some polyatomic molecules, the bonds could be polar, but because of the specific geometry of the molecule as a whole might not be polar. So you're only talking about diatomic molecules here. Next, if the molecule is heteronuclear and the bond is nonpolar, the molecule is also nonpolar. And examples of these are these two here. Check these. They're less than 0.4 difference in electronegativity. Here you're going to have some examples here again to do practice. Polyatomic molecules. Now, polyatomic molecules refer to those that have more than 2 atoms in the molecules. All right? And there's some statements here you want us to pay keen attention to. To know whether a polyatomic molecule is polar or nonpolar, it is important to know the following. 1. whether the bonds within the molecules are polar, and two, very importantly, the geometry of the molecule. We have alluded to that just now. In polyatomic molecules, the bond within the molecules may be polar, but the molecule may still turn out to be nonpolar. The reason for this is due to the molecule's unique geometry. Now you do molecular geometry for polyatomic molecules. There is this concept of what is called the valence shell electron pair repulsion theory, Vesper theory. Okay, we'll read and we'll explain, okay? According to this theory, the valence shell electron pairs on the central atom will repel each other as far away as possible to minimize the electrostatic force of repulsion between them. In these polyatomic molecules, you're having a central atom. Let's say you're having CH4, for example. In CH4, you have 4 hydrogen atoms there, right? And they're bonded to the carbon atom. Remember that a covalent bond is negative, it has negative characteristics. Now, negative will repel negative. So if I have negative bonds around the central atom, they will not want to be close to each other because of their negative character. They will try to push each other as far away as possible to minimize any tension that might exist between them if you bring them together. What are valence shell pairs? As can be recalled from a study of covalent bonding, it is the valence shell electrons of the central atom and those of the valence shell of the peripheral atoms that are involved in bonding. Recall that in carbon, when you make methane, for example, or you make ammonia, for example, nitrogen, 3 of the nitrogen's valence shell electrons bonded with 3 hydrogen atoms, each having 1 valence shell electron. So that is what we mean by valence shell electron pairs. Between the central atom and every peripheral atom, a pair of electrons is involved in bonding. We know about that already. These bonding pairs of electrons, bond pairs they call them, along with any lone pair of electrons on the central atom are referred to as the valence shell pairs. So if you recall, at NH3 has three bonds there, and there's a lone pair too. So together, all of these are called valence shell pairs. The bonded one and the lone pair there. Why do valence shell electron pairs repel? I've spoken about that already. Maybe you can read it. As can be recalled from a study of covalent bonding, covalent bonds are highly negative and would thus repel each other sideways if placed close enough to one another. Lone pairs of electrons are also highly negative and will repel each other as well as other covalent bonds present next to them. This repulsion between covalent bonds and lone pairs of electrons will determine the direction in which the peripheral atoms in the molecule with respect to the central atom. This spatial orientation of atoms will thus determine, the molecular geometry of the molecule. So look at this guy here. We're going to use CH4 to illustrate this concept. Okay? So here you're seeing carbon with 4 bonds around it. 4 sets of electron pairs. 1 pair here, 1 pair here, 1 pair here, and these will be called bonding pairs. Right? If you had NH3 here, you get 3 of these, and of course nitrogen here, and that lone pair here. You'll have 3 bonding pairs and 1 lone pair. This molecule has 4 covalent bonds, or 4 valence shell electron pairs around the central atom. Since each is highly negative, we shall draw an electron cloud for each of the 4 bonds separately as follows. So what's what happens? These are the orbitals for the hydrogen. Remember we said they're spherical in nature. And these are 4 orbitals for carbon. In the grade 12 chemistry, you'll be told that these are called 4 hybrid orbitals of carbon. And they're shaped like this. Hybrid orbital. But for now, I just want you to know that from the central carbon atom, There are 4 of these that are coming off from the nucleus. So when you bond now, if I want to take each one of these orbital here and bonding with one of these orbital here, I'm going to have 4 bonds like this. This is CH bond, a CH bond. So you have 4 CH bonds, right? Molecular geometry of polyatomic molecules, we do the AX4 type of molecules. Now we're talking about those 4 bonds. Since each of the 4 bonds formed between hydrogen and carbon is highly negative, and if they are placed around the central carbon atom, they will repel each other mutually until the electrostatic force of repulsion between them is least. In a molecule, they have freedom to move away from each other, to come closer together. So here now, this is what's going to happen. And this is where they can go the farthest apart. Each of these bonds here will go 190.5 degrees away, in every respect here. And this is space filling model, and this is the ball and stick model here. If you were to push any one of these closer together, they wouldn't stay because they will repel each other to go back like that. So the only geometry that this will have will be where you have central atom here, and the rest, the hydrogen atoms, will be around it in this fashion here. And this is called a tetrahedral arrangement. The geometry of this molecule will be that of a tetrahedron. When describing any molecule, the letter A is used to denote the central atom, and the letter X is used to indicate the peripheral atoms, or atoms. Subscripts are used to indicate the relative number of atoms of A and X respectively. The above molecule will be described as an AX4. AX4, A is the carbon atom, has 1. When there's 1, you don't put it there. And X4 meaning that you're having 4 other atoms. In this case, it is the hydrogen atoms. All AX4 type of molecules will have a tetrahedral arrangement of electron pairs and will have the geometry of a tetrahedron. Now we'll do AX3 E-type of molecules. So let's do ammonia. Of course, this is the Lewis dot diagram for that. Remember I said when you draw these things, you don't leave these dots at the end here. You take them out. You're all just using those dots here to count the number of electrons. That's what it is there. Well, how would you describe this? AX what? This A, okay? And X will be 3. But now because of this lone pair here, you have to indicate that there's a lone pair here, since lone pairs are also essential in determining molecular geometry too. So you have to indicate the lone pair here. So it says AX3E. Next, we'll try to determine the molecular geometry and the arrangement of the electron pairs around this molecule here. Well, what will you do from first principle? To get to this, I decided to start with this CH4 molecule because this is the basis for our understanding of all the other type of molecules that will come. AX3E, AX2E, and stuff like that. So this is your methane molecule here, okay, CH4. I'm showing you how in this one here, the same thing is happening here. You have a pair of electrons being shared here. But it's also here, we're only concerned with that because one of that is going to disappear soon. So that is the molecule there. We'll try to change this to ammonia molecule. Ammonia is NH3. This is CH4. We want to make this NH3. So what we'll do here is, we know ammonia has a lone pair here. So we'll remove this hydrogen here. So that will be a pair of electrons that is unreacted, and we change this carbon here to nitrogen. See? Two differences. Remove the hydrogen, and now we're left with a pair of electrons, and we now change the central atom here to become nitrogen. What do you think will happen with this guy? These will condense here to become a lone pair. Okay? I just wanted to show you how the electron pairs will be arranged. See, this lone pair that's going to be formed here will be exactly where this guy was. So the electron pairs will be exactly like what that one there is. Only that this one was like diffused a little bit there. Now you're going to get your lone pair here. See, look. This bond that was there will collapse and a lone pair is going to form here. So you see what happens? The electron pairs will have the same arrangement like that of methane, where you say electron pairs have tetrahedral arrangement. But another thing happens here, because this lone pair is close to the nucleus here, is closer to these bonds here, they'll have a greater influence on these, so they'll be repelling these a little bit closer together. That's why this bond angle will change from 109.5 to 107. So this is how ammonia is. If I had given you ammonia and told you that, oh, electron pairs are tetrahedral, you wouldn't understand that. That's why I broke it down gradually from methane to ammonia. So you can see how the bond will disappear there, how that bond will form a lone pair here, and how this lone pair is at the same position where that one was before. I explained that already. You can read it back for you, see it makes sense. Listen to this. Any AX3E type molecule in any of that, since the electron pairs, bond pairs, and lone pairs have a tetrahedral arrangement around the central atom, the molecule will have the geometry of a trigonal pyramid. So when you do this now, if you make the ball and stick model here and you take a picture of that, you get what is called a trigonal pyramid. Electron pairs, tetrahedral arrangement, but the geometry now is that of a trigonal pyramid. CH4, tetrahedral arrangement of the electron pairs, tetrahedron. Ammonia, tetrahedral arrangement of electron pairs, trigonal pyramid geometry. AX2E type molecule. We'll use water to exemplify this. You draw your Lewis structure, you have this. Here you're having two lone pairs. To arrive at this molecule, we'll start with ammonia, which is an AX2 type of molecule, and gradually change it to water that it resembles closely. We try to gradually change this here to H2O. So what we'll do, we'll take one of these bonds there, and then we'll remove that hydrogen to show you where this lone pair is going to be. It's going to be exactly where this bond was. So we'll collapse that now finally. And then look what happens. You end up with two lone pairs here. That's not difficult to follow. But one thing you ought to know is this. Because this other lone pair is here, you have two lone pairs now pushing down on these. These are negative, these are negative too, these are negative, these are negative. It's going to push these bonds a little bit closer together. So the bond angle here will be equal to 105 degrees. Okay? So the more lone pairs you have in a molecule, the smaller this bond angle becomes. So anytime you have AX2E2 molecule, right, it's telling you, look, I have a central atom here, and I have two bonds there, and two lone pairs. Because of these repulsion here, it's not going to be a straight molecule. If you didn't have that, it would be a straight molecule if you didn't have the E2. But these two lone pairs here are pushing these guys down there to create that bend shape there. AX2 type of molecule. See? There's no lone pair here now. We'll use carbon dioxide molecule to illustrate this concept. So with the carbon dioxide, having done the Lewis dot diagram for this, we put this, as you can see, it's a linear molecule. The obvious thing is to make it linear. Sometimes kids and students make it V and stuff like that. As they understand this more, they'll see the wisdom of making it a linear molecule. Some important points to note here. In this case, you have multiple bonds. You have double bonds between these two atoms here, okay? Now, when you're ascribing shapes to these molecules, multiple bonds are considered single bonds in determining molecular geometry. Even though you have a double bond here, you'll have to consider that as a single bond. Okay, you see later on that becomes important. So right now we can assume we have two bonds only there, right? Since multiple bonds are considered single bonds, this molecule can be considered to have only two bonds. Also, since the central atom has no lone pair, the molecule is classified as AX2 type. The logical geometry of this molecule is linear, as the bonds repel each other as far away as possible sideways with a bond angle of 180 degrees. No lone pair here. No lone pair here. So, had there been a lone pair here, what would happen? If you had a lone pair here, what would have happened? It will push that bond out because lone pair has negative influence. So this will not be 180. A lone pair here will cause this guy to come down a little bit more. And this bond angle will be less than that. AX3 type of molecules, we use boron trihydride for that. Alright? So first what we do is we will draw the Lewis dot diagram. I can see we have boron with 3 hydrogen around it. Okay, now people may want to say, how come I'm having only 3 bonds there? Something seems to be wrong. 2, 4, 6. This boron we are only accounting for 6 electrons. Okay? Aluminum and boron, because they're from group 3A periodic table, they're said to be electron deficient elements. So they can go around bonding things, right? That will not give them the octet, but they'll have 6 electrons over there. They're said to be electron deficient. So that's normal for them. Think about putting 3 negative things around here. How would they fit nicely without having any stress or strain? How would they fit when you have them as far away as possible, that there's least repulsion between these? This one here will be having bond angles of 120 degrees here. That's the only way that you can arrange those bonds with the least stress being experienced between those bonds there. And the bond angle there will be 120 degrees. It will be a trigonal planar molecule. There's no lone pair here. What happens if you put a lone pair here now? If you put a lone pair here, we'll start to push those guys down there. So it's not be a flat molecule anymore. Okay? It's going to be trigonal pyramidal. Alright? It'll be like ammonia. That's an AX3 type of molecule. So the electron arrangement is trigonal planar, and the geometry will be a trigonal planar geometry too.